Hi there, this is Jude Socrates. Welcome to today's video on infinite series, where we will talk about the calculus of power series representations. So in our last video, we talked about the algebra of power series representations. In other words, if you have two representations, let's say, how do you add them together? How do you multiply by a constant? So today, we are going to perform calculus on these representations. So what does that mean? We will take an existing representation, and we basically have only one example, and that is the geometric series. And we will take the derivative or the antiderivative of both sides of this equation, and that will give us a new representation. So let's go to section 3C of our textbook, and we'll see what's going on there. All right, here we go. So basically, everybody knows the sum rule for derivatives, and that is if you have a function made of two functions added together, then the derivative of that function is simply the sum of the two derivatives. There's a product rule, there's also a quotient rule, and a difference rule. But let's focus on the sum rule for derivatives. In a representation, though, you have an infinite sum. You're going to infinity. So how does that mean for the derivative? Well, fortunately, the principle generalizes to an infinite sum. But in order to prove it, we need something called uniform convergence. So we're not going to go through the details. Let's see what this theorem says. So we start with a representation. F of x equals summation n from 0 to infinity, c sub n, x minus a to the power n. And we know that when you're inside the interval of convergence where you do not include the endpoints, then the power series absolutely converges. And we will say that this power series will be exactly equal to the function at that point. That limit function is continuous and differentiable on the interval I. So, what are we going to do? We're going to perform a differentiation and an anti-differentiation. For all x in this interval, where you have absolute convergence, the derivative of the function on the left must be the summation n from 1 to infinity, n times c sub n times x minus a to the power n minus 1. So you would recognize that if you're taking the derivative with respect to x of each term in this series, c sub n is just a constant, so we leave it alone. But by the power rule, you drop the n, so there's an n times c sub n now, and then you decrease n by 1, so you have power n minus 1. Now, if you're being observant, that starts at 0, but the series starts at 1. Okay? Now, why did we do that, or why can we do that? Well, at n equals 0, you simply have c sub 0 x minus a to the power 0. But something to the 0th power is just 1. Okay, and remember, we're making an exception for 0 to the power 0, just in case. That's also 1. So you just have a constant c sub 0. So when you take the derivative of that, poof, it goes away. And your first term will be c sub 1 times 1 x minus a to the 0, or simply c sub 1. So therefore, you can start the infinite series at n equals 1 instead of 0. Could you start at 0? Yeah, sure, but why would you start with starting index that will just give you 0? Okay, it's like you just wasted your time there. Similarly, if you take the antiderivative of both sides of this equation, but of course we attach the dx for formality, then what's going to happen? You will integrate each term one by one. So the power rule says, constant, leave it alone, x minus a to the power n plus 1 divided by n plus 1. That's what we see over there. And this time, we do have to keep the starting point at 0 because constant will turn into a power of x, single power of x. When you take an antiderivative, remember there's this plus c that we encourage you to include in your answer. Some of us are more lenient than others. But this time, it's going to be important because if that's not there, how do we know that this will really be equal to whatever function that we get there? So in other words, we will have to solve for c. All right, so again, unfortunately, we only have really one example of a representation, and that's the geometric series. Okay, so summation of x to the n, and from 0 to infinity, will converge to 1 over 1 minus x for every x inside the interval from -1 to 1, for every x between -1 and 1, not including the endpoints, of course. And remember that we allowed x to be 0, even though technically when we started out with the geometric series, we said, okay, r should not be 0, otherwise it'll just be 0 plus 0. Okay, so, but now, because we're dealing with a function, we will allow x to be 0. Notice when that happens, all the powers of x will be 0, except for x to the power 0, which will be 1. And when x is 0, you get 1 over 1, which is also 1. So they match. Okay, so given this representation now, we will take the derivative of both sides. Okay, we're back to basic calculus. We'll need the power rule and the chain rule. Okay, so think of 1 over 1 minus x as 1 minus x to the power -1. Drop the -1, subtract 1 from the power, you'll get -2. Chain rule, don't forget the chain rule. The derivative of negative x, or 1 minus x, is -1. You got two negatives here that they cancel. You get +1. 1 minus x to the -2 is more naturally written as 1 over x squared in the denominator. Okay, so how about the right side? So power rule. Think of the derivative as just take the derivative inside the sum. Okay, we're basically interchanging the summation and the derivative operation. Power rule, drop the power and subtract 1. Okay, and again, we can start at n equals 1 instead of 0, because at n equals 0, that's just going to be 0. Okay, so now, what are we going to do? We're going to set them equal to each other. So we get the representation. Let me scoot over here. On the left, 1 over 1 minus x quantity squared. On the right, n x to the n minus 1 summed from 1 to infinity. Okay, so when we do these operations, either differentiation or integration, we're going to stay inside the open interval. Okay, the theorem doesn't say what happens to the endpoints at -1 or +1. Okay, so it's possible, and we're going to see more of this later, that if you plug in one of the endpoints, you might now converge when before you diverged, or maybe now you diverge whereas before you converged. Okay, so what happens? Well, when n equals 1, x equals 1 rather, sorry, you're dividing by 0, so we still reject x equals 1 like we did before. How about -1? So you're okay now, you'll get 2 squared, but -1 to the n minus 1. Okay, -1 to the n minus 1. As n goes to infinity, this doesn't go to 0. You'll get, let's see, if you start at 1, that's going to be 0. So you're going to start out +1, -2, +3, -4. You're not going to 0. So by the divergence test, the power series is divergent. And so the domain is still from -1 to 1. No change. Okay, now, I don't know about you, but yeah, here we have n, here we have n minus 1. Wouldn't it be more beautiful if you have x and, I'm sorry, start over. Wouldn't it be more beautiful if you have nx to the n and not n minus 1? Okay, this is a perfectly good equation, but it's kind of like, you know what, you have a little smudge over here. Well, how do you turn this into just n? Well, one way to think about it is x to the n minus 1 is the same as x to the n divided by x. Okay, so to get rid of the divide by x, multiply both sides of that equation by x, and so we get this more beautiful representation. X over 1 minus x quantity squared is summation n from 1 to infinity, n times x to the n. All right, so we have a new representation now, admittedly derived from the old geometric series, just like we did when we did partial fractions. We still made use of geometric series. Spoiler alert, this will change in the next video. It will get more interesting. Okay, let's go to our workroom and see how we can make use of this representation. Okay, so here's a copy of that representation that we just found. And we want to use it and something else that we know in order to find the exact sum of this infinite series. So I'm saying it will converge, and I want you to find out what the exact value of its sum is. Okay, so we can ask Maple, if we do 100 terms, that should probably be good enough, right? What is the sum of the first 100 terms? It's about 1.4375. All right, so when we get the exact sum, we will see if it matches our data over there. All right, so what are we gonna do? Well, I don't see an x to the n here, because if we're gonna use this formula, they better. Oh, but wait a minute. There's a 3 to the n there, and there's a minus 1 to the n plus 1 over there. Okay, so yeah, admittedly, there are two possible choices for an x to the n. Okay, of course, just for x. X could be either 1/3 or minus 1/3. Okay, because we have 1 over 3 to the n, so x to the n will be like 1/3 to the power n. Okay, but there is an alternating factor here. Well, there's no alternating factor there, is there? So I think we need to fold in the minus 1 with the 3. All right, so let's get to work. So let's try x equals minus 1/3. Since there is no alternating factor in the representation above. Okay, so yeah, we obviously have to use this representation. And you see that there's a 5n over there. That is how this representation will become relevant. Okay, so let us fold in the minus 1 to the n with the 3 to the n. Okay, so steps. Break down minus 1 to the n plus 1 as minus 1 to the n times another minus 1. Okay, so now we can take out that minus 1 completely out of the sum. It's just a constant. And now we have minus 1 to the n over 3 to the n. Let's do one more step. Okay, so now we will put, let me do this. Let me take that numerator and put it on the left, and we will put the minus 1 to the n in the numerator. Okay, see what I did? 5n plus 2, scoot to the left, minus 1 to the n, make that the numerator. Okay, so these two have the same exponent, n. All right, so we can put them together into a single power of n. Okay, so we can write this as the fraction to the power n of, let me copy this and remove the n's. Over here, minus 1. And let me put the minus to the left. Here we go. So that's minus 1/3 raised to the power n. Okay, so now it looks like our representation where we have x to the power n. Okay, all right, so let's keep going because we have the n over there, but we also have the +2. Okay, but remember that we also have two properties of the algebra of power series that we can use. We have additivity and homogeneity. Okay, so what does that mean? We are going to break up this single summation into two summations. Okay, it's just like integration or differentiation. Okay, break up the operation, but there's a -1 outside, so careful. We're going to put parentheses or brackets. I prefer square brackets because maple looks kind of ugly when you use round parentheses. Square brackets are more elegant. Okay, so we will break this up into the 5n term and the 2, the +2. Okay, so there you go. 5n plus 2, quantity minus 1/3 to the n. Separate the 5n and the +2. You now have two infinite series. Okay, so now we can use the representation above. Yeah, let's copy it. Okay, so want this part. And by the way, our x is minus 1/3. Minus 1/3 is within our interval of convergence, so we are allowed to plug in minus 1/3 into our representation. Okay, so we know that that is true. That equation works if x is between -1 and 1. So we can plug in x equals minus 1/3. All right. So if you do that, then we're going to get, oh, wait a minute. There's a 5 there. So sorry, forgot about that part. We can put the 5 outside, and that is called homogeneity. 5 outside, and we can also put the 2 outside. Homogeneity applied twice. Okay, so now we have nx to the n, where x is minus 1/3. So on the left side, we get, plug in minus 1/3. So in the numerator, we get minus 1/3. And in the denominator, we're doing 1 minus x. So minus 1/3, we get 1 plus 1/3. Okay, so oops, that x should be gone away. Okay, so minus 1/3 in the numerator, and in the denominator, 1 plus 1/3 is 4/3. So we get 4/3 squared, and we know how to do that. That's 16/9. Clean up. So that's 9, and that's 16. Flip it over, and you get -3/16. Right on? Okay, right on. Okay, 9 and 3 minus 3/16. All right, so this portion of our series is exactly -3/16. But what about this one? Okay, do you recognize what that is? Do you know the name of that? So how about this guy? Okay, so that's just x to the n. That's just the geometric series. Okay, there's one small detail though that you may have missed. That's almost everyone misses it. This starts at 1. In the formula for the geometric series, it should start at 0. X to the power 0, which is 1. Okay, so we have to make an adjustment. So this is just the geometric series, except it starts at n equals 1. Okay? So to make it start at 0, we can do it in two ways. We can factor out a 1/3, a minus 1/3 rather, and then the rest will start at 0. Okay, so here's what I mean, okay, because this part, a lot of people get confused. This goes from 1 to infinity. Okay, so if we look at the first few terms, you'll get minus 1/3 to the 1, plus minus 1/3 to the 2, plus minus 1/3 to the 3. Let's stop at minus 1/3 to the 4th. Okay, it goes on, of course. So if you factor out the minus 1/3, we'll take one copy, we're going to have left 1 plus a minus 1/3 to the 1, plus a minus 1/3 to the 2, plus a minus 1/3 to the 3. Okay, you see that? Take away one of these, you're left with 1 here, and 2 here, and 3 here. So you factored out one of them. Okay? Of course, this goes on forever, right? So eventually, right, you're going to get the infinite series over there. And we basically just factor out minus 1/3 from the whole series. Okay? So minus 1/3 to the n. I did not capture the n. There you go. We can think of it as factor minus 1/3 on the outside. And now, this part over here starts at n to the power 0. Okay? So that becomes minus 1/3. And we are allowed to use the formula for the sum of a geometric series, 1 over 1 minus r. So this should feel familiar because we did it over there. Okay, 1 minus minus 1/3 is 1 plus 1/3, which is again 4/3. So you're gonna get 3/4. Is that right? Yeah, so that's 4/3 down here. And it flips over to get 3/4. 3 goes up, 4 stays down, and we get minus 1/4. Minus 1 over 4. Okay, now, if you don't trust what I just did, and can I blame you? Well, we checked the whole thing, so let's check the part. Okay, so what if you just go 100 terms? What are we gonna get? Negative 0.25. I was right. Minus 1/4. Okay, so we know the two parts. Okay, the first is minus 3 over 16, and the second is minus 1/4. All right, we are ready to put them together. So we stop over here. And let's put it over here. So continuing from our last step. Okay, so we have this, and this is equal to, okay, so we have minus 1 still there, and this portion we said is this, minus 3 over 16, okay? So let's put, let me put a fraction, minus 3 over 16. I'll include the minus sign. 5 times negative 3 over 16 over there. And we have 2, and we said the second one is minus 1/4. So, you know what, I can keep that one. That's more clever. Minus 1 over 4. Right there. Okay. So, what do we get? Okay, so now the rest is just arithmetic. Let's see. You have a minus 15 over 16 here. And then minus 2 over 4, so minus 1 half. Minus 1 half. Okay, so we're almost there. Almost there. So all those minuses. Okay, I'm tired of the minuses. Get rid of that, and that, and that. Okay, so everything is positive now. Common denominator of 16. We don't need 32, we just need 16. So what do we need? 8 over 16 is 1 half. 8 plus 15 is 23. Ooh, 23 over 16. Are we going to get 1.4375? And boom, thank you very much. I don't have to make any corrections. All right, so that is the exact sum of our infinite series. All right, before we go back to our PDF, in one of your assignments this week, you're going to repeat what we did in the PDF on this new representation. If you take the derivative of this equation, both sides of this equation, by the power rule, that's going to drop. You'll get n times another n, n squared, and then x to the n minus 1. Okay, so again, that n minus 1 doesn't match with the n, so we will multiply both sides of that equation by x. You're going to get something different on this side because you know how to do the quotient rule, the chain rule, the power rule, and all that. So in your assignment, you are going to do something like this. How will you find the exact sum of something like 7n squared plus 5n plus 2? Okay, if you had one more term, because you're going to get an n squared there, you now have 3 representations to work with. This one, the one with n squared, and the geometric series. How will you find the exact sum? Haha. All right, so on that, let's go back to the PDF, and we're going to get, I believe, 2 more representations, and they're going to be important because they relate to 2 functions that we are well familiar with. Okay, so to be totally honest with you, and if you're already tired of hearing my voice for the last 27 minutes, you can just go to the PDF and read what is over there, because I'm going to walk through it and maybe give some explanations off on the side. So instead of taking the derivative of both sides of this equation, which is what we did to get nx to the n, we're going to take the antiderivative of both sides. We will integrate both sides. Okay? To integrate 1 over 1 minus x, though, we need a small u substitution. U will be 1 minus x. There's a minus. Du is, excuse me, minus dx. Okay? So that will be 1 over u minus du, or minus ln of absolute value of u. And so we get minus ln of absolute value of 1 minus x. That's our antiderivative. Oops, there's a plus c. Okay, but that's not going to be necessary because on the right side, we will have the plus c. Only one plus c is needed. They don't cancel, by the way. Okay, method. Oh, I'm just going to take both. Okay, it doesn't work that way. Okay, but x is between minus 1 and 1, so 1 minus x will be between 0 and 2. So we don't really need the absolute values. All we need is that ln. All right. So integrate the right side, again, power rule. You have summation n equals 0 to infinity, x to the n dx, which we will integrate. By the power rule, we'll get x to the n plus 1 over n plus 1. And then we have a constant. Okay, so that's where the plus c goes. And now, let's think about this. You start at 0. 0 plus 1 is 1. 0 plus 1 is 1. And n plus 1 and n plus 1 are exactly the same. Okay? So if we start the series at n equals 1, meaning we're shifting the index to start at 1 instead of 0, then this will just become x to the n over n. To check that your shifting is correct, plug in the new starting term, 1. X to the 1 over 1, which is what we get when n is 0 here, x to the 0 plus 1 over 0 plus 1. Don't you think this looks much simpler than this thing? Why do we need all those plus 1s? We don't. Get rid of them. Okay. So now we have this representation. Minus ln of 1 minus x, the left side, is a constant plus summation n from 1 to infinity, x to the n over n. Okay, so we need the value of c, and this is true for all x from minus 1 to 1. Let's plug in 0. Okay, so we get 0 to the n over n starting at 1. So nothing survives in the power series, but there's still the plus c. On the left, you have minus ln of 1 minus 0, which is ln of 1, which we know is 0. Ah, very good. So c is just 0. That's good. That c simply disappears. Will it always disappear? Most of the time it will disappear, but you'd better check. Okay, so now let's check the endpoints. You know what? Let me not scroll too far because, yeah, we need to plug in 1 and minus 1. Oh, wait a minute. If x is 1, ln of 0, sorry, still undefined. But when x is minus 1, we get minus 1 to the n over n. Okay. And on the left side, we get minus ln of 1 plus 1, ln of 2. So we get minus ln of 2 or ln of 1 half. Okay, remember, minus 1 goes up as a power. Okay. So we get an alternating series on the right, and let's see, our Bn is 1 over n. We've seen this before. This was actually one of our first alternating series. Okay, so both sides are defined. All right, so we now have a bigger, slightly bigger domain. We can include -1, but we still cannot include +1. So this is the series that will allow us to compute ln when x is between -1 and 1. In other words, this will be between 0 and 2. Okay, so we have this representation, and it might look a little awkward to you. Why are there two minuses? Minus ln of 1 minus x. And don't you dare cancel the two minuses, by the way. But that's okay. So on this right side, it's not alternating. It's simply x to the n over n. And just for good measure, let's look at, I guess that's E4, I'm sorry, S4, the partial sum up to x to the power 4. We have 4 terms. And if you graph both minus ln of 1 minus x and that partial sum, you'll get two graphs which are almost the same, can't be different, you can't tell them apart near the origin. All right, so before we finish with this example, we said that we get this power series, alternating series, equals ln of 1/2 or negative ln of 2. Well, if you don't like the ln, I don't blame you. Turn it into positive ln of 2. We need an extra -1 in the numerator, so it's now -1 to the n plus 1 over n in the summation from 1 to infinity. Okay, this was probably the first example that we got, that we saw in that section on alternating series. And I don't have to say probably because it does say here, it is the first example. Okay, and we said that the exact sum is, yeah, it was about 0.68 something. ln of 2 is 0.6931, blah, blah, blah. So yeah, that is the exact sum of that alternating series. Okay, I believe this is our last example for this section. We will now look at the arctan function. Okay, something very different, not geometric, not logarithmic. We want arctan. So the basic idea is that the antiderivative of 1 over 1 plus x squared dx is the arctangent function, plus c, of course. Okay, so this looks almost like the geometric series, 1 over 1 minus u. Okay, so to get plus x squared, our u should be minus x squared. All right, so plugging this minus x squared into both sides, you get minus x squared to the n is 1 over 1 plus x squared. Right there. Okay, so that is the basic idea. In that section where we talked about the algebra of representations, we just plugged in x squared. Okay, you can go back and look at that example. It's on the first page. But now, because we want 1 over 1 plus x squared, we want to substitute minus x squared. Okay, so we are going to simplify this. The domain is the same as we have there. It's still between minus 1 and 1. And now, rules for exponents. Minus x squared quantity to the n is the same as minus 1 to the n. X squared becomes x to the 2 times n. Not x to the 2 to the n or x to the n squared, nothing stupid like that, okay? It's x to the power 2n. Okay, so there is actually, that's pretty good looking representation right there. But it's more useful if you integrate both sides now. Okay, the antiderivative on the right will be the arctangent function. We'll put the plus c over here on the left. Or is it going to be on the right? We're about to find out. Okay, so yeah, you can put it on the right as well. Okay, so antiderivative on the left, power rule, x to the 2n becomes x to the 2n plus 1 all over 2n plus 1. And coefficient stays the same. Don't touch it, just copy it. Antiderivative of 1 over 1 plus x squared is the arctangent function. Okay, very good looking. Now all we need is to solve for the plus c. What is the c? So again, you can plug in any number between minus 1 and 1. The best number, almost always, pick the center. Pick 0. Arctangent of 0 is 0 because tangent of 0 is 0. Remember that part. Okay, 0 to the power 2n plus 1. N starts at 0, so 2 times 0 plus 1 is 1. Okay, 0 to the 1 over 1, that's just 0. Everything dies here when x is 0. Arctangent 0 is 0. So guess what? C is once again going to be 0. It's always nice when that happens. Okay, so let me keep going over here. So the left side is 0, the right side is 0 plus c. C is simply 0. What about the endpoints? Okay, all bets are off as far as the endpoints are concerned when we differentiate both sides or we integrate both sides of a representation. That's why that theorem is stated only in the open interval. Okay, so let me scoot here. What happens at the endpoints? When x is minus 1, we have minus 1 to the 2n plus 1, but that's even, so minus 1 to the 2n is just plus 1, and we just get minus 1 to the 1, or minus 1. Okay, so we get minus 1 to the n times minus 1 over 2n plus 1. Okay, we can put these two together. Ooh, we get a nice alternating series. And we know that the b sub n, 1 over 2n plus 1, is monotonic decreasing. It goes to 0. So this converges to, this converges by the alternating series test. Okay. But on the left side, on the right side rather, you have the arctangent function. Arctangent of minus 1 is negative pi over 4. Okay. So what about when x equals 1? So this time 1 to the 2n plus 1 is just 1. So we get another alternating series, minus 1 to the n over 1 times 1 over 2n plus 1. So there's only minus 1 to the n, no plus 1 this time, over 2n plus 1. And on the other side, we have arctangent 1 is pi over 4. Oh, wait a minute. It's really the same equation, okay, because we have an extra minus here and an extra minus here. Okay, so we get really the same equation involving pi over 4. All right, so we can now include both left and right endpoints, minus 1 and plus 1, to the domain of this representation. Okay, so once again, we can confirm through GeoGebra by taking only 3 terms, because only odd powers are expressed by 2n plus 1. So even with just 3 terms, you get a high power already, x to the 5 over 5. Alternating, x minus x cubed over 3 plus x to the 5 over 5. Here is our partial sum, and here is the gorgeous arctangent function, of course. But our representation is valid only between -1 and +1. Ooh, so guess what? Arctangent 1 is pi over 4, which is approximately 0.8 or 79 something. Okay. But of course, this is slightly higher than that point. Okay. They don't have to exactly match. They won't. Okay. So speaking of endpoints, we said that we get pi over 4 as the arctangent of 1. Okay. So yeah, this formula gives us pi if we multiply both sides by 4. All right, so here is a very elegant formula for the number pi expressed as an infinite series. Start with 4, subtract 4/3, so you'll get 3 1/3, 3.333. Okay, I'm sorry, 2.66666, yeah, minus 4/3. And then you add 4 eighths, 0.8, subtract 4/7, add 4/9, minus 4/11, and so on. You have the odd integers in the denominator, 4 in the numerator, alternating, plus minus, plus minus, plus minus, and so on. So if you actually compute these partial sums in GeoGebra, you're going to have to wait a while, though, right? 0 to 99, 3.13. Okay, that 3 is wrong. 0 to 999, 1,000 terms, 3.14. Okay, that's nice. But we know that pi is like 3.14159. Okay, so 10,000 still, that should be a 159. Oh, finally it's 15, but that's an 8. Okay, so yeah, this is a gorgeous formula. This formula right up there, but unfortunately it doesn't converge very quickly. Okay, you definitely don't want to do this by hand, right? But still, it's nice to know that we can compute pi to as many digits as we want by taking more and more terms of this alternating series. And remember, we do have a formula for the error of an alternating series by approximating it using a partial sum. Okay, so if you know that you want pi to 100 decimal places, that error formula can tell you, okay, if you want an accuracy up to 100 decimal places, you're going to have to compute maybe 7 gazillion, just kidding, 7 billion terms or something. Okay, it can be done. All right. So that is our video for today. I hope you enjoyed it. And next time, promise, we won't have to rely on the geometric series for everything. We are going to start with functions that are important, that we know from all the way from pre-calc and trigonometry. Ooh, spoiler. And we will see how to create power series representations for them. All right. So until next time, I hope you enjoy the rest of your day. Bye.